So we looked at the world of carbohydrates. Now we're ready to move into the next classification of biochemicals, and that would be our fats and oils. So I want you to see where these come into play in our everyday world, but first let us look at what constitutes a fat and an oil. All right? Fats are solids, and we use the term solids for fats. Oils are liquids, okay? And they are, for us, very efficient ways of storing energy. We can store fats in our body. We don't store the oils in our body, but on the shelf we can store these fats and oils and have a effective way of storing energy for later consumption. All right, so they are less oxidized than the glycogen, so you can get more energy from them when you use them. So in our body we can store glycogen, okay, but we can also store fats, and we get a lot more energy out of the fats than we will get out of our oils. There's a lot more, so yes, and the glycogen, as we talked about in our carbohydrate unit, is a carbohydrate, okay? That's how we store fat, as a carbohydrate. You can store it for short-term energy storage as glycogen, but you can store it as long-term as fats. Okay? Now, 1 gram of fat contains 9 calories of energy, whereas for our carbohydrates, you can only get 4 calories out of 1 gram of carbohydrate. So it's all because of this being less oxidized. It gets a lot more energy as it goes to the process of turning into carbon dioxide. So some of our foods that are high in fats are things that a lot of people know about, because we're a real calorie conscious community, all right, of people. We try to make sure we're watching our weight, and people are always talking about counting calories. But the things that are high in fat aren't necessarily bad for you, but you just need to be aware they've got a lot of fat in them. So our nuts, cheeses, did you know avocados have quite a bit of fat? It's a vegetable that has quite a lot of fat in it. Now we know that fried foods, not necessarily fried fish, but fried foods are high in fats. We fry them in oil, or we fry them in Crisco, which is a fat, and we'll talk about that later. Now, there's a difference between the word we use for fat and the word we use for fatty acid. Subtle differences, but fatty acids are a part of our fat language. So let's talk about fatty acids, all right? If you have a carboxylic acid, now we saw this group when we were in our organic world. Carboxylic acid. We know it has a C, a double bond O, an OH group, and then continue over on this side with hydrogens or carbon, either a hydrogen or a carbon chain. Okay? So that is a carboxylic acid. When that R group, okay, when what is after this carbon and going off in this direction has a lot of carbons in it, then we quit calling it just a carboxylic acid and we start calling it a fatty acid. Okay, so we would have 1 or 2 dozen carbons coming off of that chain, and that would be a fatty acid. So stearic acid is a kind of fatty acid, and look at how many carbons it has. Now, I haven't used this notation very often, where we have grouped a bunch of CH2s together, but what this is saying is I have a repeating of 16 CH2s, and then I have a CH3 for my N group, and then my carboxylic acid group. So if I were to draw it out, you know, and as a line structure, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 16, 17, 18. There's the 18th carbon. This end has got the double bond O and the OH, and that would be what stearic acid would look like. It has 18 total carbons, 16 are CH2s, and then we have the end one down here, which would be a CH3, and the one over here, which is a C double bond O, OH. So look how little oxygen there is. There's a lot of carbons and a little bit of oxygen over here. Now, carbohydrate, we know it's got the CH2O general structure, right? For every carbon, there's an oxygen. Well, this is not true for fatty acids. We have a lot of carbons and just a couple oxygens, okay? Now, natural occurring fats fatty acids, I should say, naturally occurring fatty acids will tend to, I don't know if it's always, but it is almost always for sure, have an even number of carbons in here. So this one up here had 18 carbons, and they might have 12 to 24 carbon atoms in them, and there's a reason for that, and it has to do with how they're constructed in a body. When you consume calories and you consume things and your body starts building these fatty acids, they have to build them 2 carbons at a time, and that gives them an even number. Saturated fats versus unsaturated fats, or saturated fatty acids versus unsaturated fatty acids, has to do with double bonds. All right? Sorry about all of that. Let's get back to here. All right, so saturated fatty acids, when we use the word saturated, it's going to have no double bonds. What it's saturated in is hydrogens. You have maximized the number of hydrogens in there, because we know that when we have a double bond present, okay, a double bond between carbons, it's going to reduce the number of hydrogens you need to fill that out. So saturated fats have no double bonds. Now, if you have a diet that is high in these saturated fatty acids, they tend to lead people to have an excess of cholesterol in their body. So there is a recommendation not to have a lot of saturated fatty acids. Okay? Look at this structure here. I mean, this chart that I have here, this graph. Notice it's the number of carbon atoms is going across the bottom and increasing, and we're starting off with a few and working our way up, and we're seeing the melting point increasing on this side. So this one, 1, 2, 3, 4, 5, 6, this one has 6 carbons, and it has a melting point down here low. What does that mean? That means if you're above this temperature, it will be a liquid. And you have to get below this temperature before it is a solid. Okay? Here is, oops, I'm having a hard time with my screen here. Okay, so here is the line for room temperature. Okay, 22, 25 degrees Celsius. You have to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons before you have a substance that has to get to this temperature before it would melt. So at about 35 degrees Celsius, if it has 10 carbons, it's going to melt. When you get up here and you've got 1, 2, 3, 4, 5, 6, well, I could probably just count. I mean, come down here. It looks like that is 18. 18 is going to take you all the way up to 70 degrees before you can melt it. So it's going to be a solid at room temperature, and it's going to be a liquid once you warm it up. Okay, so the melting point adjusts with the number of carbons. Now, we saw this when we were discussing hydrocarbons. When hydrocarbons get longer and longer, their melting point increases. So does their boiling point. It increases. Those things increase with the number of carbons. So this is applying the same way here. Now, when you start adding double bonds, we can put one double bond in there, or we could put many double bonds in there. We have the term unsaturated, okay? So if it contains a double bond, we call it a monounsaturated fat. If it contains more than one double bond, it is a poly. So one is mono, more than one, we get up to many, okay? Polyunsaturated. Now, very often, they could have 3, 4, 5 double bonds within the molecule, depending upon what kind of fat it is, okay? Fatty acids, it has that C double bond O, OH group on the end, okay? So that's what it says there. If it's more than one, we suddenly call it many. I don't know why 2 is many, but in the world of unsaturated, 2 or more is many double bonds. So here is an example. This is a naturally occurring fatty acid. We see the acid in, so that makes it a fatty acid. It has a double bond in there between 2 of these carbons, and it would be a monounsaturated fatty acid. Now, I want us to, I don't think I have it popping up down there. No, I want us to practice drawing the line structure of that and thinking about where the double bond is, but let's not worry about the double bond yet. Let's count how many carbons there are. We have 1 plus 7 more, that's 8. We have 9, 10 plus 7 more, that's 17, and then 18. We're back to, again, 18 carbons. So let's draw 18 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 carbons. This last carbon has got the C double bond OH on it. Now let's figure out where to put the double bond. The double bond is between this carbon here and this carbon here. Let's number that, okay? So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's the next 7. So this is carbon 9, carbon 10 from this end, okay? Or we could have numbered from the other end, which is more typical, but that's okay. I numbered from this end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, and 10. So I would put my double bond right there, and that would be oleic acid. Oleic acid is a monounsaturated fat. Linoleic acid, okay, it looks like oleic acid, but it has a little extra prefix there, linoleic acid. It has 2 double bonds. Now it is still the same number of carbons, all right? 1 plus 4 more is 5, 6, 7, 8, 9, 10, and 7 more is 17 and 18. But it's got now 2 double bonds. So this becomes a polyunsaturated fat. Now, what do I want you to know from this? I do not want you to memorize the name that goes with the structure. What I would like for you to do is, if you saw this, recognize it and be able to classify it as a monounsaturated fat. Okay? Monounsaturated fatty acid. Let's use the whole language. Fatty acid. Fatty acids have this N group. The fatty part means it's got lots of carbons. The monounsaturated means it's got a double bond right there. The bottom one, I would like for you to be able to recognize that and see it as a polyunsaturated fatty acid. And I would like for you, this goes back to what we learned in organic chemistry, if you saw this, you could translate it as a line structure, and if you saw the line structure, you could translate it into its condensed structural formula. Now, we need fatty acids in our diet, unsaturated fatty acids. So we a lot of times give fat a bad rap and say, oh, you got to have this low-fat diet, but it's not a no-fat diet. You need these unsaturated fats in your diet if you're going to have a healthy diet. So there are sources of good fats that we can consume, and we don't want to consume a whole lot of them. Now, am I the poster child for only eating unsaturated fats? No, I'm not. Am I somebody who really limits it to a very small amount? No, I'm not. But I am aware that that is a goal, okay, is to limit how much fat you take in, but not to go down to 0. Okay, so what's the difference between a fatty acid, oopsie, what is the difference between a fatty acid and a fat? Okay, fatty acid and a fat. Well, a fatty acid is a fat is when you take a fatty acid and add the molecule glycerol. And now we're going to be able to use not the word acid with it, but we can use the term fat and oil with it. So what is glycerol? This is a molecule that I expect you to know. You do need to learn this. It is a 3-carbon alcohol. Notice it has 3 OH groups. We did talk about this in your lesson on alcohols, what glycerol is. So glycerol is a backbone of this molecule. What you do is you take that glycerol and you take 3 fatty acids and you do a reaction that we learned how to do when we were doing our organic unit. We learned to take out a water molecule and link these together and form an ester. We practice that as a group activity. So there is a water molecule that could be removed. There is a water molecule that can be removed. There is a water molecule that can be removed. So we are pulling the water out, okay, and linking them together. The name of this reaction is a condensation reaction. okay? Or a dehydration. Now, usually when you link together by pulling water out, we call it condensation because you're bringing it together by removing water. So on the right side, what we have is what's called a triglyceride. Sometimes it's called a triester. Can you see the ester? We have the C double bond O. We have the O, and instead of having an H here, we now have a carbon there. And whatever this long group was on our fatty acid is the long group that we see right here. And then, of course, the water molecule. So you're forming a triglyceride, and triglycerides are what our fats and oils are. Okay, so sometimes people, when they go get blood work done, will have their cholesterol checked, but they also will get their triglyceride levels checked. And these triglyceride levels are these fats and oils that might be in your blood. Okay, so let's look at fats and oils a little bit more. In general, your fats come from animal fat, and your oils come from plants. Okay, so that is the generality. Let's think about sources of animal fat. If you take the cream off of milk and you shake it, you make butter. Butter is a solid, okay? So that is an animal fat. If you were to cut into a nice ribeye and you know, you've got a ribeye steak there and you have those pieces of fat in the ribeye steak, that is a solid. So those are generally where fats come from, is from your animals. So we'll talk about why that would be. Oils are generally fats that come from plants. So cottonseed oil, corn oil, canola oil, which is actually rapeseed oil. They don't call it that here. They call it canola oil because nobody wants to talk about rapeseed. So those are plants that produce oils. And so that's the general trend. So why would that be the case? Let's look at why it is the case. So we talked about how if you increase the number of double bonds, you are going to increase the melting point. So we had a trend of that, and we saw a graph of more and more carbons, higher and higher and higher the melting point. Well, if everything else is equal, meaning the number of carbons are the same, okay, if the number of carbons are the same, then adding those double bonds into that is going to lower the melting point of the fat. So what will that do? If you have, let's say, a 18, let's do the stearic acid, 18 carbon chain, okay? It is going to be a solid if there's no double bonds. Now you start adding double bonds to it, maybe 2 or 3 double bonds in there. What this is going to do is lower the melting point. So if you had 18 carbons and no double bonds, okay, it would be a solid at room temperature. But if you had 18 carbons and let's say 2 double bonds, so it's polyunsaturated, then it would be a liquid at room temperature because you lowered the melting point. You brought the melting point down below room temperature, and that is going to make sure that it will be a liquid at room temperature. So why are animals giving you the fat, the solid, whereas oils are coming from the plants? They are the liquid. It has everything to do with the double bonds. Animal fats tend to be saturated. What does that mean? That means no double bonds. And we're dealing with stuff like stearic acid that I described right here. Okay? Animal fats have no double bonds, so they tend to have higher melting points, and that would make them a solid at room temperature. So you're going to have higher melting points than what the plants have. The plants are unsaturated, so they have one monounsaturated or multiple double bonds. Okay, and that's what you have in plants. Generally speaking, having fats from plants, eating an avocado that has a rich fat content, or nuts that have a rich fat content, are going to give you those unsaturated fats, and they tend to be healthier fats for us. So here is why the double bond is going to cause that melting point to change. If things can pack together nicely like we're seeing here, here is a saturated, no double bonds, saturated fat. They can line up nicely, and when they can line up nicely like that, that is going to cause it to be easier to form a structure and get into the solid state. Okay? But when you start adding the double bonds, they don't have these nice straight chain possibilities. The double bond causes them to kink up a little bit, and they don't have the same shape. And so then they cannot pack together as nicely. And when you can't pack together as nicely, that is going to lower the melting point. They cannot get into its, the presence of, let me read what it says. The presence of the double bond prevents the fatty acid chains from packing tightly together. So these guys cannot pack tightly together. It's going to make them more difficult to form a solid. Okay, it's hard to get them to form the solid. So you have to bring the melting point, you have to bring the temperature down lower and lower and lower before you can get them to come together as a solid. And that is why they stay as a liquid at room temperature. Here is a comparison, okay? We have got things, and they're showing the pink is saturated fats, okay? The dark green is monounsaturated fats, and the light green is polyunsaturated fats. Now we're looking at a whole list of different fats here. I don't want you to memorize this, but we want to look at the trends and see how it's playing out. Look at canola oil. Canola oil here is from a plant, and look how high in unsaturated fats it is. It is one of the best oils that you can use because of its high unsaturated content. It has a mixture of fats, and some of them are saturated, but most of them are not. If we come down here to cottonseed oil, it has a little bit more in the world of saturated fats. Peanut oil, a little bit more in the world of saturated fats. But when do we start getting into, we'll look at coconut oil here in just a minute. It's a plant fat, but boy howdy, it's got a lot of saturated fat in it. But here are our animal ones. Okay, our animal ones, we're starting to really jump up in the world of having saturation. Animal fats tend to be higher in saturated fats. Now, tend is the word. Coconut oil is really, really, really high in saturated fats. Coconut oil is not an oil at room temperature. If you go to the store and purchase coconut oil, it will be a solid. Now, it's short chains, and it doesn't take a whole lot to melt it. So you can take that coconut oil and you can just run it between your fingers, and it will easily melt. You can have a warm day in your home and sit it on the counter, and it will melt. So it melts at a fairly low temperature, but it is definitely a solid at room temperature. So coconut oil would be your exception to the trend. The trend is plants are high in unsaturated, and animals are high in saturated. Okay, so I'm going to end you with that slide. We've kind of got the general idea of what a fat and oil is. Fats and oils are made from fatty acids linking together with glycerol. The fats are the liquid, the oils are the solid, and now we know generally why. It has to do with unsaturation.